We've got a lot of announcements today, but they're all kind of here. We'll just go over them individually in just a moment. Oh, neat. Not completely sure. Yeah. Now that's a cool expression right there. That is the polar representation of a number in the plane. Yeah. E pi I. Well, it looks like it's time to start. Welcome back, everyone. We've got a great deal of announcements to get through today, but before all that, any questions folks would like to discuss to start us out? Okay, well, it's going to be a pretty busy weekend. The major thing I'm going to be working on is just getting caught up in grading. Once I have your exams graded, I'll be posting the grades into Moodle, and I'll let you know so you don't have to check Moodle compulsively over and over. I'll email everyone once the grades are uploaded. Also, what we have going on is we're just about to finish section 8.2, and 8.3 on polar coordinates, that's going to be the last section for the entire semester. So this is a pretty interesting section as well. It's also dangerous. Polar coordinates seem like a novelty in a trigonometry class. And then you move into Calculus 1 and you'll never talk about polar coordinates. Then it comes up in a big way in Calculus 2 and an even bigger way in Calculus 3. So it's one of those things where you're learning it for the first time in trigonometry, and it's almost guaranteed it gets reviewed in a calculus class, since it's something that has a long separation before it comes up again. So this will be our opportunity to discuss it for the first time. We'll get into this section a little bit today, but we'll mainly be finishing it when we come back next Tuesday, the 23rd. But because that's the last section for the entire semester, 8.3, once we finish it, we're just going to immediately convert into reviewing for the final exam. We'll have a lot of extra documents down there in the Moodle website, additional review problems, as well as old final exams from the past to give us a feel for what we're getting into. But that's what's going on in section 8.3. That'll be our last section. And it also means this was a weird section for us because I can't assign a homework section on that one. The problem is if I assign a homework section on 8.3, I would be collecting it on finals week, which is usually considered bad form. I don't like to collect homework on finals week unless it's late work. So what I'm going to be doing instead is just post a list of suggested problems, and I'll post solutions as well, so you can use that as a way to study for that last section. Because it's also the very last section of the course, I'm not going to ask anything too major out of there. You'll see some of the more basic kind of questions. And I'll give a bunch of hints as well as we're going through them of what would qualify for a pretty good final exam question. So that's what we're going through for the content at the moment. Then there's a bunch of extra credit opportunities. We'll look at them individually. So let's maybe go in reverse order. The first extra credit opportunity is more just that I'm accepting late work for full credit. So if life got busy, if work got too out of control, anything like that, it absolutely happens, probably to everyone in class, then don't worry about it. If you send in whatever homework is late, check in the Moodle system for any assignment that's missing, or just email me. If you get them in by the day of the final exam, I'll accept them for full credit. So that's the last day to get in any missing work. Aside from that, there's also this one. In my opinion, this is the most important extra credit opportunity. And there's a reason I like to post this one, really a couple reasons. Back in the day, around 2010, I used to give extra credit opportunities, which were like these additional assignments, like extra content that we didn't even study in trigonometry. But that didn't really help people, I noticed. It turns out if I encourage people to just study really hard on the final exam, that's the most important extra credit opportunity ever, since that's going to affect your score quite a lot. So the way this one goes is, if you score well in the final exam, so well that your final exam grade is larger than the minimum score amongst exams 1, 2, and 3, then your final exam score will replace that minimum score. If it doesn't, then it won't hurt you. So this is extra credit. It's not going to drop down your grade. But that's what we'll do for that opportunity there. Any questions about that so far? Okay, another thing I want to mention about final exams is that I don't get into a habit of writing the nastiest final exam possible. My goal is not to cut people's grades down. I will be the one writing the final exam for this class. And if it does turn out to be a hard exam, there's one thing I always look at. I look at the average grade for the whole class before the final exam and the average grade for the whole class after the final exam. People's grades dropped by 3%. I typically do curve the final exam to bring it back up. I'm not trying to move the average grade down. I want it to be about the same after a good final exam. So there's the potential that this exam is curved. And if I do curve it, the extra credit opportunity is relative to the curved grade. The curved grade is what will replace your minimum grade among exams 1, 2, and 3. That's a lot of talking though. Let me pause for a moment. We do have a question. Jamie asks, if our exam 1, 2, and 3 are good, do we still take the final? Yes, we are required to take the final exam. It's more of a math department requirement. It's like a formality. Other questions so far? Okay, and for the last extra credit opportunity, this is more for the math department. The math department is trying really hard to get course evaluations, and they've been struggling to do that. And so trying to help out by offering extra credit if you do the course evaluation. I've been doing this for years. I don't know if it's been helping since they've been threatening us that they're going to do in-class observations if we don't have enough course evaluations. I'm actually not afraid of that. I've never really had anyone else here observing the class. That'd be kind of cool. But just to help them out, here's how you can do this extra credit opportunity right here. You first have to find the course evaluation. You might see right away why the math department's struggling to get these course evaluations. It's not even easy to find. They wouldn't happen to know where it is just by curiosity. Exactly, good call. There's a bunch of stuff right here. I don't mention it because I don't put anything in there. I don't use anything there. But this arrow is actually a whole tool that you can open up, and it shows a bunch of weird things like activity, completion progress, announcements, and it's right there on the bottom. Let's see if we can fix that. So let's move it to the top. And I mean, it's still hidden in there, and I lost it. There it is. It's still hidden, but that's how you find it. So when you go to do your course evaluations, go to the Moodle website, click open the block drawer is what they call it. And this is the link that takes you to the actual course evaluation. Couldn't have made it any easier, right? So that's maybe one reason why they're not getting evaluations. And if you click on it, you get something that looks like it was written by the legal department. It says, the State Board of Education requires that students be allowed to evaluate their courses and their instructors. And that's absolutely true. The State Board of Education mandates that to us. We're a state college. So if we didn't give you the opportunity to review the class and the instructor, well, the State Board of Education would come down with an axe and make sure that, well, a bunch of people would have new positions probably. But this is the math department's way to encourage you to do the evaluation. I don't know if that's the best encouragement, a big block of text, but I guess that's their way of saying it's important, I guess. But if you click this on this right here, you're going to be doing the evaluation. It takes about 15 minutes. When you get to the very end of it, it'll just say, thank you for doing the evaluation. If you take, say, a cell phone picture of that or a screenshot, email it to me, and that will get you the extra credit. I didn't say what the extra credit was. Let's take a look. It's a little bit different in all of my classes. The extra credit for the evaluation for this class would be that I will drop 2 additional homework assignments at the end of the semester. We're already dropping 2, so that will make it a total of 4 out of a total number of assignments, 13. That's a pretty substantial extra credit, but I actually think it's fair because homework, you're just learning the concepts. It's natural to make mistakes here and there, or maybe quite a few mistakes when you're learning stuff that happens. So dropping assignments at the end of the semester, I think, is a natural thing to do. So that's all the extra credit opportunities. Any questions, folks, with either one? Okay, so beyond that, our final exam has been finalized. And it's kind of awkward because, again, this is 2 classes running as one, really, but For the people who are registered in the in-person section, Math 1144, Section 02, the final exam will be held in this room from 8 p.m. to 10 p.m. The registrar is to blame for this, so that's the person you want to write the angry letter to. That's a really rough time. We'll get through it, and it's because of that time slot. I don't like to write a nasty exam, and that's another reason I curve the final exam. That's not us working at our best, 8 to 10 p.m., just something we try to get through. If you're registered for the fully online section, like all of your other exams, I have to send your exam to the Pocatello Testing Center. I'm going to be trying to do that as soon as possible. And once I send your exam to the Pocatello Testing Center, I'll directly email you like before to let you know you can contact them to schedule your exam. So that's how it's going to work in the two different classes. Any questions or comments at the moment? Okay, so again, for the in-person section, we will be in this room, 8 to 10 p.m. We'll just get through it. Sorry about that weird time. For everyone else, it'll be in the Pocatello Testing Center. And for the far remote students, we'll be doing the proctoring that we did for the other exams, like before. Well, this is the sample final exam problems, but we will be adding additional documents here before you come back to class on Tuesday. And additional documents, again, when we do a review on Thursday. That was like 10, 11 minutes of announcements. But any questions at all, folks, with any one of those? Okay, well, we've got about a section and a half to go, so congratulations, we're nearly through trigonometry. Let's get back into the law of cosines where we left off. I think it was like example 3. Yeah, there it is, example 3. Example 3, I think, is one of the coolest examples in trigonometry because Heron's formula is extra special. Let's first look at the problem, and then we'll discuss Heron's formula. It says, use Heron's formula to find the area of the triangle with the given information. We've had multiple formulas for area of a triangle, but notice what's lacking with this information. There is no angle there, and that's a big disservice, because if there was an angle, you could go to section 8.1. The area formula there that developed the law of sines could potentially have been used. But here's our triangle. You could use that, yes, but then you'd have to find the height, which means you need to look into the angles of that triangle. You could find them with the law of cosines, but that's also a lot of work. Or all you wanted was the area. Heron's formula doesn't care if you have angles or not. That's the remarkable thing about that formula. So if we have A is 12.4, B is slightly longer, 13.7 in feet, and C is 20 feet. So we want the area of that triangle. And like you were saying, Michael, this could be done by dropping down a perpendicular. But then you need to know the height of that perpendicular or use law of cosines. There's a lot of ways to get the area of this triangle. But in my opinion, the slickest, fastest, and definitely kind of a cool way is that formula up above. Well, taking a look at this, it says Heron's formula. So if we kind of research this a little bit and type out Heron, we get this, but this is not what we're talking about. We're not talking about the bird. Let's put in Heron's formula. We're talking about, when we say Heron's formula, oh, where's Wikipedia? Here we go. Oh dear. I found the link once that I'm trying to look for at my office, but if you Google somewhere else, apparently you get something different. Let me say Huron, Greece. There it is. So it was this guy who came up with the formula, the hero of Alexandria. Kind of remarkable because this is now going back to 70 AD. These people were absolutely a lot smarter than you might think. We think in our modern times that with all our cell phones and technology that these ancient people were not necessarily as smart as us, but that's absolutely not true. With very, very minimal tools, this guy developed an extremely remarkable formula for calculating the area of this kind of stuff right here. So thanks to Huron, the hero of Alexandria, we have some interesting tools. And a lot of math came from the ancient Greeks back in the day. This is just one of those examples. So to me, that's what makes this kind of a fun problem. So much like Pythagoras, this is a next new interesting old guy that's been dead a while that gives us some new tools. You only use Huron's formula when you have this information, no knowledge on the interior angles. So calculating the area could be hard without that knowledge. We don't know the height of the triangle either. But Huron's formula says the area is this. Well, that's a weird looking formula. It first involves S. It's the sum of all the sides divided by 2, called the semiperimeter. And once you have the semiperimeter, let's see if we can blow this up a little bit. You throw that value of S here, here, and here. You subtract all the side lengths. Oh, I missed a S, but it's also right there. You subtract all the side lengths that's provided. That's going to be these. And you get the area of the triangle right away. Let's give it a try. Step 1, calculate S. So S says, sum all these values right here. Where's my red dot? There we go. So it's going to be 12.4 plus 13.7 plus 20. Oh, that's a 20.2. Let me fix that there. Divide the whole thing by 2. Now it's a so-called semi-perimeter. It's kind of a weird definition as well. And I forgot I need a calculator. We all need one. Let's grab one. Okay, so first, the computation of S is going to be 12.4 plus 13.7 plus 20.2 halves. So it comes out as a 23.15. So that's a step 1. And the last step 2 is us just writing down the answer. It's really that quick to get the area of a triangle if you know all of the side lengths. So the area is now the square root of. Following the format, we just take S, 23.15. Then we're going to multiply by, oh, let me double check. I've got a 12.4, 13.7, 20.2. Yeah, I'm still getting the 23.15. That's probably my fault because I wrote it down as a 20 first on the triangle by mistake. Then I had to sneakily fix it. So that's probably my fault there. So the next will be, we go inside here and we just use the semi-perimeter 3 more times, but subtract the corresponding side length as well. So 23.15. I'll just go in order, subtract A first, minus 12.4. Multiply by 23.15. Subtract 13.7. And we're almost there, 23.15. Subtract 20.2. So this alone gives us the area of the triangle exactly. Well, we'll do some rounding after we put it in the square root potentially. So here's our last step. Down over here, call the square root function first. Let me make that a little bit longer. Then really it's just as fast as you can type this into your calculator. 23.15, 23.15 minus 12.4 times 23.15 minus 13.7 times 23.15 minus 20.2. Comes out as at 83.29, and we're completely done right at that step. Any questions so far, folks, at the moment? Okay, one question you might have had is that this is basically one step and then calculators, the rest of the whole problem. So why write down all of this? Well, if this was a real final exam question and you made one mistake right here, let's say I made this mistake. I forgot a decimal. It's undefined. Let's say I made this mistake and put the decimal here or something like that. If you reported 222.91, and that's all you gave me, I lost any basis for partial credit on this step. If you showed this step, what's about to go to the calculator, I will award essentially all of the partial credit. Even if you made a mistake right here, I might take off like a half a point, or even sometimes I've taken off a quarter of a point on a final exam. But show this on paper on the real final exam, and you're getting a massive amount of partial credit. 83.2. Oh, I got that as well. I was more showing if you made a mistake here, you're getting something weird, but show it on paper, you're on the right track. Yeah. But let me put it back to the real answer. Yeah, I got the 83.29 as well. Yeah, sorry. Oh, no worries. That's a lot of buttons to press. So that's the reason I say try to put it down on paper. On a final exam, it's easy to mess up something here because I would be stressed out typing things into a calculator. So this gives you tremendous partial credit. It's 83.29 feet squared. So that's a really fast computation for the area of a triangle. And if this was a final exam question, you even have a bit of a check on it. Here's how we would check this answer. Let's suppose that we really had a height. Let's say that the height is 13.7. It isn't because that's not 90 degrees, unfortunately. But if it was, the area of this triangle is 1/2 base, let's say 12.4, times height. That's not the height, but it's approximately equal to it. We calculate it that way, that's the wrong answer, but it tells us that answer is in the right ballpark. We should be getting something close to, if we used the basic formula for the triangle incorrectly, we're still in the right neighborhood of the right answer, 83.29. So that kind of check can be valuable, again, especially if you make this kind of mistake and report that answer, you at least have a way of knowing, hey, that's not even feasible. That's way, way out of line. Well, we did it, folks. That's a fast problem. Any questions about it? Okay, I'm not even completely certain why our book put this problem here, but I think it's a pretty cool formula. We've had a lot of area formulas so far, so this is just an additional one. Then going down below, this will be our last problem for the section 8.3. It's another law of cosines problem, so that's, I think, a great idea to look at law of cosines one more time. And the problem says, a surveyor has taken the measurements shown in the diagram below. So we've had careful surveying work right here. We want to find the distance across the lake. So I would imagine this is the lake we're talking about here. There's weird things inside there. But our whole goal is to find this distance d. This diagram isn't too complicated, so we can just leave it as is. We have a nice triangle with an interior angle 70 degrees, opposing sides. This tells us we can use law of cosines directly. It goes like this. You relate one side with its angle in law of cosines. So it'd start by saying d squared equals, then you use these values next. It's going to be 800 squared plus 900 squared. Then the immediate thing to put down in law of cosines is go -2 times 800 times 900. So you use those values twice. And you multiply them by the cosine of that angle right here, 70 degrees. So this is essentially the pattern of law of cosines. We relate one side by squaring it with the cosine of the opposite side, throwing it in there. And you just drop in these other values in those positions. That means this problem is just about done as well. You're going to next throw all of that into the calculator in that format. You might take the square root after or take it all as one step, up to you. I would usually personally break it up into 2 steps. But any questions at all, folks, on getting this line right here? Okay, so this is the big takeaway of the problem. That's essentially law of cosines. And when it comes to writing the final exam, you might have noticed section 8.1 had a problem about like this. Section 8.2 does as well. I'm not going to throw a bunch of problems like these, but there should be an expectation of something like this is going to be on the final exam. either from section 8.1 or like the one you see right here. Next step is just all calculator work. So let me know if you're getting different values and we'll figure it out and diagnose. But the immediate first step we should check out is, let's put our calculators into degree mode because we have degrees produced. You can convert it to radian, but if all your information is in degrees in these sections, that's the better mode to use. So let's see here, 800 squared plus 900 squared minus 2 times 800 times 900 times cosine of 70 degrees. We should be getting 957,490 and a little bit of change. Any questions, folks, to that step? Okay, let me see how many digits I can memorize. 957,490.99. I do not actually have a really great working memory when it comes to copying, so let me double check. Hey, I think I got it. Now, I need to take a square root because I didn't do it on this line. You're welcome to just do it all at once if you put the square root there. But I'll go SQRT 957,490.99. That's a pretty accurate answer with 0.99. Only these digits changed. And we are rounding our answer to the nearest tenth. So it looks like the distance across the lake is 978.5 feet. Almost said miles. That would be a really big lake, wouldn't it? So we did it, folks. If that's 800 feet, 900 feet, the 978 feet looks like it's in the right ballpark. And this is a great use of law of cosines. This is a case where law of cosines is extremely fast, much like Huron's formula was. You can calculate and just get a distance out. Any questions whatsoever, folks, on that process? Okay. Well, congratulations, folks. We just completed the penultimate section of the course. Last thing we need to do is take a look into polar coordinates, and that one will be our last one for the semester. Again, I can't assign any homework for this one, so what I'm going to be doing before we come back on Tuesday's class, I'll have some sample problems here out of the book. They'll all be odd exercises, so those would be the ones you'd want to practice for the final exam. And here's our last section for polar coordinates. Again, this is always a pretty weird spot to be in trigonometry because polar coordinates is important. It comes up a lot in calculus settings, Calc 2, Calc 3, comes up in engineering settings as well. But a lot of times you learn polar coordinates and then you might not use it for like a year and a half until you're in calculus 2. But despite that, let's take a look at how it goes. Reading through the definitions, we have some graphs that we want to fill in as we go. It says, in this section, we'll introduce the system of polar coordinates that can be used to locate points in the plane. So these are alternative coordinates to the XY coordinates, or Cartesian coordinates, or rectangular coordinates. All of those are synonyms. This is, for a lot of people, probably your first coordinate system that's different than the XY plane. We start by drawing a half line or ray called the polar axis. This is actually how the first day of class started. We wanted an initial ray and a terminal ray to define angles. So it's kind of an interesting overlap. So here it goes. We put in a heavy dot for the pole. The polar axis we usually draw as a horizontal line emanating from the right. And this will be O, capital O, for the origin. So this is the polar axis going this way. And we have it as a horizontal line emanating to the right. Now, it's supposed to help us locate any point P on the plane. So let's drop down a point to emphasize. Let's say our point P is here. It'll have XY coordinates, but we're more interested in what are the polar coordinates of that point. First thing we need to do is find a distance from the origin, the pole right here, to that point. Let's give that a color. The other thing we'd probably do is draw another line. that emanates through there. And from here to here is the length r. So we have a distance from the point P to the origin. That's not quite enough to specify the point, because the next thing we need is the angle theta is going to tell us how much we should rotate off the polar axis to actually arrive at that point P. So theta goes right here. And the more you look at this, this really does look like the first day of class when we were defining an initial side. That would have been this. A terminal side would have been that. That's how we define the angle on the very first day as well. So the angle goes there. And now we have two things. A distance, a directed distance r, and the angle. Put those together, and you have the polar coordinates of P, referred to as r theta. So we'll say here that this point is r, the distance away from the pole, and theta, the amount you have to rotate to land right on that point P. Any questions about that so far, folks? Okay, whatever we need to emphasize, it's a polar coordinate we're giving. I'll often say that we're dealing with polar coordinates just straight out, or I'd write r theta equals like 5 pi over 2, just to emphasize those are polar coordinates that we're producing. Now, there's a weird thing that goes on as well. What are the polar coordinates of the origin? Well, we would say 0 because it's a distance 0 away from itself, but that means the point's overlapping on itself. You could put any angle theta right here. So it could be, say, 0, 0, if your angle is 0, but any angle is going to do the job. So that's the same as 0, 0, same location as 0, pi over 3, and so on. And this now shows us something weird about polar coordinates. There are infinitely many different ways to describe every point in the plane if you're using polar coordinates. Why is that? Well, we rotated by theta to get to P, but what if you did this? That's theta plus 2 pi. So this is also r theta plus 2 pi. And it could have been 2 pi k. K could be positive, negative as an integer. And that's always going to land you at the same exact spot. That's kind of a, not necessarily a defect of polar coordinates, but it is kind of an uncomfortable reality that Cartesian coordinates have a unique description for every point. Polar coordinates do not. There's infinitely many ways to land on the point P. So there's some trade-offs here. But before we get too far, let's also take a look at this information here, because there's more than one way to specify this point, not just by changing the angle, but also by changing r. R could be positive or negative or 0. That's why we refer to it as a directed distance. Let's put down a really quick example right here just to explain that further. Before that, any questions, folks, with the main diagram up here? Okay, polar coordinates already looks like an adventure, but it's one of those things that we just have to get through because it comes right back in mathematics. I mean, most of the trigonometry that we've studied does come back the further you get into calculus courses and so on. So the next thing we're going to look into is what's going on with those 2 points right here. Let's plot a simple example to start. We've got a pole, a polar axis, and I want to plot, to begin, r theta equals, let's make it be 3. And how about pi over 3? Just a random example. So how would we plot this point? You'd want to start with the angle pi over 3. We know that's about 60 degrees, so it comes up and out like this. We typically like to indicate the angle this way, not so much doing this every time, because those kind of little angles start to make the diagram just too busy to look at. So we just paraphrase by saying, this is pi over 3 measured from the positive polar axis over here. So once you have the angle down, we need to go a distance of 3. So you begin by putting down 1, 2, 3. And that's the point we want to land on. This is 3 pi over 3. Well, that's our first polar point that we plotted. Any questions at all with getting that down here? Okay. In a way, it kind of is, but actually what R is going to turn into is this right here. It's actually x squared plus y squared using Pythagorean's theorem by default. So if we're relating R to the Cartesian coordinates, that's what it truly is. Kind of weird in a way. But this gets even more uncomfortable because I could put a -3 there and still land right on this point. Really kind of bizarre, but let's show how to do it. There's another angle that goes along with pi over 3. It'd be going this way. This angle is 4 pi over 3. If you think of your unit circle diagram, that's all we're pulling out is just various angles from that diagram. And if we say that r theta equals -3, 4 pi over 3, we plot it slightly differently. So let's go back to this definition here. We'll adhere to the convention that r theta and -r theta plus pi represent the same point. R can be both positive or negative now. And so if you're plotting this point, you go to 4 pi over 3. But the distance is negative, so you go backwards, the diametrically opposed direction, 1, 2, 3. You just land right at this location. So this turns into equals -3, 4 pi over 3. But notice that theta plus pi is just going to be pi over 3 plus pi. This turns into pi over 3 plus 3 pi over 3, which is the 4 pi over 3. So that information there is actually factually accurate in the sense that add your pi to your pi over 3, you're getting the 4 pi over 3, but you're not going the positive direction here because you're looking at a negative. That means go the other way, up 3, and you land at the same exact spot. So that's what they're saying here. R theta is also -r theta plus pi. Pi over 3 plus pi is 4 pi over 3. So I feel like this is the next most uncomfortable thing about polar coordinates. You can have infinitely many different values for the same point by changing theta, adding an integer multiple of pi, 2 pi, or you can just change the directed distance r to a negative value, add pi to it, and you're still landing on the same exact point. Definitely weird, but any questions so far about any of that weirdness at the moment? Yeah, go ahead. Yeah, we would do, if it's 4 pi over 3, we would normally be walking along that, but if it's negative, you go the directly opposite way, which is back to pi over 3 as well. So lots of weird stuff. And in fact, we'll take advantage of this actually when we're converting between polar and rectangular coordinates. We actually need to use this idea shortly on these notes, probably next Tuesday, looking at the clock. But let's take a look next at that other concept. Well, as soon as you develop a new coordinate system, you want to have a relationship between your old coordinate system and the new one. So that's what this is going to do. It gives us a set of systems to take a point P in Cartesian coordinates, x, y, and relate it to the polar coordinates. These are the relationships that you would build. But before we just take that as fact, let's do some explanations here. Let's begin by putting down a polar axis just like before. I'm going to put down just an arbitrary point, so it's going to look like this. This will be some r theta. We don't necessarily know what it is, but here's our polar axis going this way. Here's the point in question. The angle theta is this ray coming out. And because we're relating it to rectangular coordinates, let's just throw the rectangular coordinates on top. It would come in like this. So now here's the XY coordinate system overlaying the polar coordinate system. So now we really are directly relating the two systems together. Let me just make this a little bit more apparent. So now, next thing you can do to get these equations to make some sense is drop a perpendicular down. There it is. The moment you have a right triangle, your gut instinct might be SOHCAHTOA is on the table, and then now it definitely is. So let's analyze SOHCAHTOA based off of this information. First thing you need is coordinates. We need a point xy. So this is also xy and r theta at the same time. So we want to know if we have a polar coordinates and Cartesian coordinates, how do they relate to each other? Well, it's all done right here. This would be a point x. So it refers to the length of this segment. Up here, this takes us to a point on the y-axis, y. So y is telling us this length going that way. And well, we need Pythagorean's theorem next, right? What Pythagorean's theorem is giving us is r right here. How would it work? Well, r is this length. It's the length of the hypotenuse, the directed distance. And so we definitely know that r squared should be equal to x squared plus y squared. That's just directly Pythagorean's theorem. So that's where this equation comes from. Let's write it over here on the margin. R squared equals the side length here squared, that would be x squared, plus the side length going this way squared, that would be a y squared. So that's where this equation comes from. That's kind of neat in a way. And we can also get this equation pretty fast because there is an angle theta right here. Just easier to actually throw it into the triangle so we can see it. Now use SOHCAHTOA, and it says tangent at theta is going to be, I kind of wrote SOHCAHTOA wrong. Let me see if I can fix that. The TOA part is TOA. O for opposite. Opposite of what? Opposite of theta. Now it's talking about this side length, which is y. So let's throw that on there. Next, you divide by the adjacent side. Adjacent to theta, that's going to be x. And that's where this comes from. It's just directly using the right triangle on this diagram. So we have two sets of coordinates already, but there's more coordinates on the left relating x and y. So we still need to explain those, but this is a good point to put something additional in the notes. When would you ever use this? You use this set of coordinates, this pair, when you're converting from xy, so rectangular coordinates, to r theta, now into polar coordinates. First equation directly gives you r, but the second equation is a trigonometric equation we have to solve. So we go back to section 7.5, using calculators and all that kind of stuff to get the right angle. So that's the purpose of those two equations. That means these ones are for this purpose. We use these to convert. Let me make sure I can put in enough space here. Those two convert r theta, so the polar coordinates, to xy, the Cartesian coordinates. These are a little bit nicer because if you have polar coordinates, you know both r and theta. This is just a computation. It's like a section 5.3 problem here and here. This one's tougher, so it's actually harder to go from Cartesian to polar. That's the challenge problem. But let's explain these two next. First, any questions, folks, with what we have on the table so far? Okay, well, back to SOHCAHTOA, we already used this up, and that's the idea about this conversion. You're using all of SOHCAHTOA. Let's go to this part. Sine of the angle theta is going to be opposite of theta. That's this segment here, x, divided by the hypotenuse. That's going to be r. So SOHCAHTOA gives us x over r. And now, or hang on, let me think of this. I think I made a mistake. X looked okay, and I think I was highlighting the right thing. But this distance is not x. That's y. I think the x there was the distraction for me. Let's see if we can correct that. Let's just start over. When you make a mistake, sometimes that's a good strategy. Just throw out the whole thing and start right over. Throw out the baby with the bathwater. So sine theta is going to be the opposite side. So this length, which is y, divided by the hypotenuse, which is r. That looks a little bit better. Now, this is an equation from which you can solve for y immediately. This implies y equals r sine theta. But that's what we have right here. Y is r sine theta. And the same exact trick is going to give us the second equation. Let's run through the motions just because we can. Why not? It's a review of right triangle trigonometry. The CAH part of SOHCAHTOA is telling us that cosine of the angle theta would be the adjacent side. That's this, which is x per side length. Divide by the hypotenuse, that's going this way, r. And now if you multiply both sides by r, you're solving for x, and it tells us x equals r cosine theta. So that's the second equation down here. So if we are trying to go from polar to Cartesians, we use those. They're nicer equations. In the opposite, we have to use these two equations. They are a little bit tougher. We'll try out both. Well, any questions, folks, so far? That's a lot to derive those two things, but these equations feel random unless you see where they actually come from. So it's always a good idea if you're looking at random mathematical information, try to draw a picture. Anything you can sketch, draw, analyze is a great way to absorb this information. I mean, the more you believe in them, the more you know where they came from, the easier they are to use, it turns out. And let's give this a try next. It says graph the polar coordinates and then convert the polar coordinates into rectangular. This is actually not too bad of a problem. I think we might make it in time. To graph that, I'd start with the polar axis. There it is. Next, plot 7 pi over 4. We can fall back to our unit circle diagram. This is pi over 4, dashed line because it's not what we want. 3 pi over 4. 5 pi over 4. And this one is the one we want to be on. 7 pi over 4 here. So we've got the angle. It says go a distance 5 along that ray. So just use a uniform tick mark. This is setting the scale. 1, 2, 3, 4, 5. So here's the polar coordinates, 5, 7 pi over 4. So that step's done. But what we also want is, what is the rectangular coordinates? So that will be an xy equals something. There's a little bit of work to do, so let's do it up here. X is going to be r cosine theta. We do have the r value. It's this right here. We additionally have the theta value. That's this, the 7 pi over 4. And so it's pretty fast to calculate. You can say x equals r, which is 5, cosine of the value of theta, 7 pi over 4. And at 7 pi over 4, cosine would be in quadrant 4, where it takes up a positive value. Although this is a polar axis, we can still visualize the quadrants on this. So this is just going to be a positive root 2 over 2. X equals 5 times root 2 over 2. Or more compactly, if you like, 5 root 2 over 2. That means back down here on our answer, we're halfway done. 5 root 2 over 2. Next, we just do the same thing. Y is going to be equal to, take up here, the distance r, which is 5 again. We're using the sine value next, so it's going to be sine of angle theta, 7 pi over 4 again. But 7 pi over 4 being a quadrant 4 tells us that sine of this value is negative root 2 over 2. So y is going to come out as y equals 5 times negative root 2 over 2. So negative 5 root 2 over 2 altogether. We drop it down here. We drop it down here correctly, negative 5 root 2 over 2. Then this is our answer. If you'd like, you can also superimpose the xy plane on top and see if that seems reasonable. 5 root 2 over 2, yeah, that's, well, at least it's positive as it should be. Negative 5 root 2 over 2, it's negative. It looks like it's plausibly the correct Cartesian coordinate for that polar coordinate right there. Well, we did it, folks. When we come back on Tuesday's class, we'll do the opposite problem. Look on an application for distances between polar coordinates. The hint on that is just law of cosines, a good opportunity to review it again. And then we'll start reviewing for the final exam. But any questions whatsoever, folks, with where we ended on today? Okay, well, we're nearly there, folks. That's kind of exciting. Have a great weekend, everyone. And if you have any questions while you're studying over the weekend, don't hesitate to write. Otherwise, I'll see you all in Tuesday's class. The polar? Just a straight line like y equals x, you're saying? Oh, wow. So you've got 10 theta for R2 theta, gives you that weird curve right there. Yeah, that's pretty wild. That's kind of hard to produce by hand, but pretty much what's going on there is you're just producing a polar curve plotted in the polar axis. Pretty fun stuff. You know, even Desmos over here, I think this even has a polar mode as well. Let me take a double check. Let's see. You've got a polar grid that you can put on here. You said differential equations? Yeah, that's definitely a differential equation there. It looks like you'd probably be plotting either a solution curve or phase space diagram, something along those lines. Sorry, say again? A differential equation? A good one could be like, say, a good one could be y prime equals, say, actually for a differential equation, maybe y double prime minus y prime equals 0 would be a pretty decent one. Maybe y double prime minus y. Yeah, that'd be a good differential equation there. Yeah, I mean, I'm not too sure either. That's a